Thank you very much. Next we have Jean-Pierre Lebreton. I understand you're the mission manager on Huygens, right? So you did not participate in ENIR.
No, I did not.
But still, it's the way I'm counting it. It's 3 landings on Churyumov and landing on with Huygens. So that's you participate 80% of landings on small bodies. Congratulations.
Thank you. Well, I'm sorry, Titan is not a small body. Titan is a big body. Medium, all right. Okay, so I'm really pleased to give an overview of the RPC, so Rosetta Plasma Consortium observations. It's really an overview, and I'm going to cover very briefly topics which are going to be covered in more detail with 8 poster presentations. So I will refer to those posters in the course of my talk. So it's a long list of people. I would like to acknowledge the COPS, the Rosina team, who has provided us with the COPS data. Catherine said this morning it's a safety instrument. It's much more than a safety instrument. It's really a very useful instrument for doing excellent science. So thanks to the Rosina team. I would also like to acknowledge the team in Toulouse, which is doing some quick look for us, and this is shown to be extremely useful, and I'm going to show some examples. I also like to acknowledge the Rosetta teams. They have been doing a great mission, and industry, which did a great spacecraft. And we should not forget industry, which really is very instrumental in our mission. And finally, I would like to acknowledge NASA and national funding agencies for payload and science support. So I've done my acknowledgement first. Okay, next slide.
Just page down.
So what do I need to? Yes. Okay, so those are the 6 instruments of the consortium. Is composed of 6 PI instruments. So from top to left to right and top to bottom. So the ion and electron spectrometer from Southwest, the ion composition analyzer from Kiruna, the Larmier probe from Uppsala, the magnetometer from Braunschweig, the mutual impedance probe from Orléans. I'm the PI of that instrument, and all of that is coordinated by the PIU provided by Imperial College London. And we are really operating as a coordinated single instrument on Rosetta. So we are really operating as a consortium. So those are the main characteristics. A lot too much information, but let me try to go briefly through. Where is the laser? Yeah. So the IES measures electron and ion distribution. It has a very wide field of view. It's covering 360 by 90. The energy range is from 4 eV to 20 keV. The ICA, ion composition analyzer, has the same field of view, covering more or less the same range, but with a better resolution. The Larmier probe, there are 2, in fact, measuring the bulk, plasma properties, density, temperature, and others. An important point, which I will refer to during this presentation, is that the lab instrument is really the instrument which provides a spacecraft potential, which is an essential measurement for interpretation of our data, but I guess also for the interpretation of some of the dust data. So the mutual impedance probe is a radio frequency probe, which also measures basically the same bulk properties of the plasma, but with a very different technique. We cover a wide range of plasma density temperatures. And finally, the magnetometer, which measures the 3 components of the magnetic field. This is illustrating the low activity comet and the interaction of the solar wind with a low activity comet. So this is borrowed from a paper by Andrew Coates. Of course, he did not know at that time we would be flying by Churyumov-Gerasimenko. It's not clear. Well, clearly this is illustrating a comet before really activity starts, possibly at 4 AU. So this is not the condition we are encountering, although sometime we are encountering such condition. But clearly now there is a coma which is developing and which is sometime an obstacle to the solar wind at times, and especially at southern latitude, the solar wind may be impinging the comet, but at times when the activity is large and on the northern side, the coma is really an obstacle to the solar wind, and it's deflecting the solar wind, and we observe that. So other phenomenon which I'm going to mention, the charging of the dark side of the comet is indirectly observed in our instrument. What else? Well, I mean, the direct sputtering of the nucleus by the solar wind, we do not observe it, but I understand that Rosina has some clear evidence of that. So this is illustrating what I was mentioning earlier, the summary, a quick look we are putting together. So I will come back to such a quick look later, but this is the electron spectrometer, the electron measurement, ion measurements. Those are the COPS pressure measurement, the mutual impedance probe, which is a radio frequency probe. This is frequency indicating plasma activities when we go through the enhanced pressure in the jet-like features. This is a Lamia probe in a fixed bias mode. This is a magnetometer, and this is, two attitude information, comet aspect angle and solar aspect angle. So this is in October from the 12th or the 11th to the 15th, and this shows an increase activity on how our data are changing when the comet activity is increasing. We clearly, well, this is the solar wind, protons and alphas. The electron intensity is increasing. We see when we go through the plumes here in enhanced signatures for the plasma, which is clearly indicating an enhanced density. But I will return to that in one of the last slides. So our observation, first of all, the magnetic field measurement, the team is really focusing on the spectral analysis, and this is a spectrum when we were in the solar wind in May. So this is used as showing the reference spectrum, and within the comet environment in September, there is clearly significant enhancement of the spectrum, and there are some very nice wave activities in the range 10 to 200 millihertz, which are really indicative of the interaction between the comet, the low activity comet, and the solar wind. So this has been converted into a song, and if time allows, I will play the song at the end of my talk. And there are two posters related to those observations. This is IES ion measurement. This is the solar wind here, so 360 degrees as a function of energy. So this is solar wind, and this is the cometary ions, much lower energy. So we clearly see them nicely. One observation which is quite interesting and maybe a sort of a discovery is that we see monoenergetic electron beam which are indicative, which are attributed to the charging, negative charging, which is accelerating those electron beams to such energies of a few hundred EVs. IS again, so this is the proton, alphas, and E plus, which is due to charge exchange between the solar wind and the coma. H minus in the solar wind, also probably a discovery. We believe this has not been seen before at comets. This is due to double charge exchange with the coma. Another very interesting detection of negatively charged nanograins. This is indicated here. and here and here. So this is covered by the poster by IES. In fact, I forgot to mention there are 2 posters from the IES team for the previous data. Let's move on. Another poster on the detection of charge, nanograin, and it goes into more the technique of the detection and the sensitivity of the instrument. So this is another poster by George Clark. The ICA, so this is also, as I said, detecting ions, but with a somewhat better energy resolution. So we see clearly proton, helium, and also and alphas on helium plus as with IS. And the low energy water ions, which are accelerated, and they are plotted here in a 360-degree plot. And you should refer to the poster by Hans Nielsen. An important objective, of course, for the plasma instrument is to measure the density. This is a bit tricky. I mean, this is work in progress I'm presenting here. So the lab measurement, we start to get sort of maps, so 2D maps. When Rosetta was at 10 kilometer orbit, so maps along the trajectories, even 3D maps, and clearly we see here, for example, the double periodicity due to the neck activity in those kind of maps. And we also see, but maybe better see here, that the electron density, or this is in fact ion density, which is on this scale here is from 0 to 50, is somewhat enhanced in the northern hemisphere. And this is further discussed on this poster here. And the same measurement with the mutual impedance probe. So this is covering a wider period from early September to almost mid-December. So we more or less see the same features. We are not, the scale is not indicated here. This is electron density. The scale is from about 50 to 300. So we are not yet in agreement regarding the plasma density measurement, but we are working on that, and I think we are converging. And this is described in a poster by Pierre-Henri et al. Just one point regarding the effect of the spacecraft potential. And the spacecraft potential, this is illustrated here. If it's positive, it attracts electrons, it repels ions, but it also attracts negatively charged nanograins. And if the spacecraft potential is positive, it should be noted that the energy spectrum detected for the electron is somewhat shifted to higher energies, and for the ions, we miss the low energy part, and vice versa for a negative spacecraft. So I think I'm running out of time, so this is illustrating some of our combined observations, so COPS, the mutual impedance probe, which is really showing a nice plasma density increase, electron density increase during the jet. And this is the lab measurement, which shows the effect of the spacecraft potential, and we can retrieve the value of the spacecraft potential from those measurements. And this is an important parameter for us to analyze in a coordinated way the lab measurement, MIB measurement, and also the IS, and also the ions here I did not discuss. So I will conclude. I will not get the singing comet unless I have time to do that. I don't.
We can get back to it.
Okay, thank you.
Any questions in the meantime?
I have one.
Yes, please.
That was a very nice demonstration of charge exchange from solar wind protons and alpha particles. Do you think you'll be able to see O plus 6 and O plus 5?
Well, I guess the question is, do you think we will see all 6
minor ion charge exchange?
Minor ions? Well, I would really defer this to the poster discussion. I mean, Jim Birch, or unless Jim, you want to answer that question, but Jim is going to discuss that further at his poster.
I heard